Hello, students. In today's lecture, we are going to learn about thermodynamics, NCRT section 11.10 to 11.11. This is disclaimer, learning objectives. By the end of this lecture, you will able to differentiate between reversible and irreversible thermodynamic processes. Then comprehend the Carnot cycle, its operation between temperature reservoirs, and calculate Carnot engine efficiency. In today's lecture, we will cover first 11.10 reversible and irreversible processes. After that, we will learn Carnot engine. Alright, so these are the topics of the today's lecture which we will learn one by one. So first, reversible and irreversible processes. So meaning of a reversible process, we can say a process which can be reversed in such a way that all changes occurring in the direct process are exactly repeated in the opposite order. Or we can say a reversible process is an idealized thermodynamic process that can be reversed at any stage without leaving any change in the system or surrounding. Alright, so suppose we run the process forward and then backward. In the end, everything, system plus surrounding, returns to its original state as if nothing is happened. It's like rewinding a movie perfectly. No frames are lost and nothing changes in between. Alright, conditions for reversibility. First, there must be complete absence of dissipative force like friction force, viscosity, etc. Second, speed of process should be infinitely slowly because the process is reversible process. Temperature of the system must not differ appreciably from its surrounding. So these are the conditions for reversibility. If these conditions are well defined, then we can say reversible process occur in very well. Examples: all slow isothermal and adiabatic processes are reversible. You know, in isothermal process, temperature remains constant, whereas in adiabatic process, there is a no exchange of heat between system and its surroundings. Very slow evaporation and condensation in a reversible process. Second is irreversible process, just opposite of reversible process. So these are the processes in which a system and its surroundings cannot return to its to their original state after the process has occurred. It means the before and after. Means initial state and final state, or we can say original state and final state are not same in this. It cannot be returned to their original state. Some key characteristics of reversible process. Once a change occurs in a system, suppose, it cannot completely return to its exact original state. Energy transformation often result in unrecoverable forms like heat from friction, leading to energy loss in this system. So suppose a process is a reversible process and there is some loss of heat energy due to friction, so they cannot return to their original state because of loss of heat energy. Examples: relative motion with friction, heat transfer across a temperature difference. So, due to the temperature difference, heat flow from a hotter body to colder body. But colder body to hotter body, it's not possible. All right. So we can say this process is irreversible process. And if we talk about the relative motion with friction, so there is a loss of heat energy. So this is also cannot be returned to their original state. Electricity flow through a resistance leading to heat generation. So this is a third example. All right. Now Carnot engine. Second law, or we can say Calvin Planck's statement, rules out the possibility of 100% conversion of heat into work. In simple terms, it says that efficiency of a heat engine can never be unity. It means the efficiency of heat engine is less than 1. Then what can be the highest efficiency possible for a heat engine working between two reservoirs? Think about it. So we can say Carnot engine. All right. So here question arises: what is Carnot engine? So Sadi Carnot in 1824 convinced an idealized reversible heat engine operating in a cycle. That engine called the Carnot. This engine is completely idealized. Carnot engine has the maximum possible efficiency for any engine operating between two given temperatures. First temperature T1 source temperature, second temperature T2 sink temperature. All right. In upcoming slides, we will deal with uh, two temperatures: source temperature and sink temperature. So, if we talk about the efficiency of Carnot engine, or we can say Carnot efficiency, the formula is eta is equal to 1 minus T2 upon T1. Here, eta is the efficiency of the Carnot engine or Carnot efficiency. And we know T2 is the sink temperature, whereas T1 is the source temperature. All right. Now, what is a Carnot engine? A Carnot engine is a theoretical engine, completely theoretical engine that operates on a Carnot cycle. And this engine represents an idealized heat engine that operates with maximum possible efficiency between the given temperatures of the reservoir. It estimates the maximum possible efficiency a heat engine can achieve during the conversion of heat into work or vice versa. It means if we have a Carnot engine, then using this engine, we can uh, take the output of maximum possible conversion of heat into work and vice versa. All right. Carnot engine works through a Carnot cycle, which is a combination of four reversible processes. All right. Isothermal expansion, isothermal compression. Similarly, we can say adiabatic expansion or adiabatic compression. So Carnot cycle. Engine operates in a cycle of four reversible processes. First, isothermal expansion. All right. The working substances, usually an ideal gases, is contact with the hot reservoirs. And in adiabatic expansion, uh, we can say uh, the system is insulated, no heat exchange. So Q equal to 0. Third is isothermal compression. The system is in contact with cold reservoir. And fourth one is adiabatic compression. The system is insulated again. In this case, the gas is compressed, temperature rises from uh, temperature of the sink to the temperature of the source. So we will learn each expansion or compression one by one. So uh, a process is not quasi-static if it is involves a finite temperature difference between a system and its reservoirs, because we know quasi-static process is a infinitesimally slow process and there is a pressure and temperature are well defined. So in a reversible heat engine, heat absorptions from hot reservoir must occur isothermally to ensure quasi-static conditions. Isothermally means the temperature remains constant throughout the process. Similarly, heat release to the cold reservoir should also occur isothermally to maintain reversibility. Remaining two processes in a cyclic are adiabatic to enable the temperature transitions between two reservoirs. All right. So let's see. These are the four reversible processes of Carnot cycle. First, we know isothermal expansion, then adiabatic expansion, then isothermal compression and adiabatic compression. So first, as shown in the figure, isothermal expansion. So on PV indicator diagram, the process is first to second. This is a case of isothermal expansion. In this case, gas expands at a constant high temperature. You know, in isothermal process, the temperature remains constant throughout the process. So here, gas expands and absorbing heat from a hot reservoir as the piston moves up. All right. Second, adiabatic expansion. So this is the second process as shown in the shown on PV indicator diagram. Adiabatic process second to process third. So here gas expands without heat exchange. Means the there is a no exchange of heat between system and its surroundings. So delta Q exchange of heat is equal to 0. So causing the temperature to drop as a piston continues to move up. All right. So here in adiabatic expansion, the system is insulated, no heat exchange. The gas continues to expand during work, and its temperature drops from source temperature to sink temperature. All right. Now, during isothermal compression, so this is a third reversible. So look at figure 3 to 4. 3 to 4. Gas is compressed at a constant low temperature. All right. And the system is in contact with cold reservoir. Gas is compressed slowly, so temperature remains constant, releasing heat to a reservoir as piston moves down. Adiabatic isothermal compression. Process 3 to 4. In adiabatic compression, process 4 to first, we can say the system is insulated again. Gas is compressed, all right, and temperature rises from cold reservoir temperature to uh, sink reservoir temperature to source reservoir temperature. So gas is compressed without heat exchange. It means the change in heat, or we can say exchange in heat, delta Q is equal to 0, causing the temperature to rises back to initial high level as a piston moves down. All right. So these are the four stage processes. Carnot engine. Steps involved in a Carnot cycle. First step here, this is isothermal expansion. So in isothermal expansion, we know temperature remains constant throughout the process. So look at here, PV indicator diagram. Pressure, initial pressure P1, final pressure P2. Volume V1 to V2, but the temperature remains same, T1 to T1. So this indicates the process is isothermal process. So here gas expands from pressure P1, volume V1, temperature T1 to pressure P2, volume V2, and temperature T2. Now, in this process, uh, heat is absorbing at constant temperature T1 from the hot reservoir, all right, and that amount of it is Q1. We consider here. So, change in internal energy is zero. Why? Because the temperature is constant. So, we know that uh, change in internal energy depends on temperature. The mathematical term is delta U is equal to NCV delta T. All right. So if the change in temperature delta T is zero, so the internal energy will also zero. All right. And the work done by the gas on the environment is W1 to W1 to second. So it will be Q1, because in this process the change in internal energy is zero. This equation comes from first law of thermodynamics. The amount of heat supplied, Q, is equal to change in internal energy plus work done. So but the change in internal energy is zero. So work done is equal to amount of heat, that is Q1 in this process. All right. So the formula to calculate the work done we already studied in previous lecture. So that is nRT1 log V2 upon V1. All right. So when we put the value of V2 and V1 and T1, you will be get the work done in isothermal process, isothermal expansion, first to second. All right, this is a very simple term. Similarly, a step second. So this is the adiabatic expansion. You know, in adiabatic process, uh, there is a no exchange of heat between system and its surroundings. It means delta Q equal to 0. But there is a change in temperature. So gas expands adiabatically in this process from pressure P2, volume T2, temperature T1 to pressure P3, volume V3 and temperature T2. So the important point here is this: in the adiabatic expansion, all macroscopic variables are changing. P2, V2, T1 to P3, V3, T2. So work done by the gas. So we know the first law of thermodynamics: delta Q is equal to delta U plus delta W. So here, uh, exchange of heat between system and its surroundings is zero. It means delta U is equal to minus of delta W according to first law of thermodynamics. So when we calculating the work done, the relation is work done second to third. It means second uh, stage to third stage. It will be nr divided by gamma minus 1 T1 minus T2. All right, and we already derived it in previous lecture. Third step, add isothermal compression. Compression here, gas is compressed. So gas is compressed here isothermally from pressure P3, volume V3, temperature T2 to pressure P4, volume V4 and temperature T2. So the important point here is to understand is this: the process is isothermal com- isothermal compression. So the temperature again remains constant throughout the process T2 to T2. All right. So in this case, the work done on the gas by the environment is uh, we can calculate by using the first law of thermodynamics. That is delta Q is equal to delta U plus delta W. But the process is isothermal process. The temperature remains same throughout the process. So their internal energy is what? Zero. All right. So heat released Q2 by the gas to the reservoir at temperature T2 is also the work done. And that is W324 is equal to nRT2 log V3 upon V4. Here Q2 is comes from the first law of first law of thermodynamics. Delta Q is equal to delta U plus delta W. The process is isothermal. The temperature remains constant. Temperature constant, change in internal energy zero. So we can say the heat is equal to amount of. All right. I hope this is clear. Now fourth step. Fourth is step 4 to first. So this is adiabatic compression. Again here the gas is compressed adiabatically from pressure P4, volume V4, temperature T2 to pressure P1, volume V1 and temperature T1. So work done on the gas by the environment for adiabatic process is Nr divided by gamma minus 1 T1 minus T2. All right. Now we have a two equation 11.18 and 11.21. So using this these two equation, the total work done by the gas in a one complete cycle is W is equal to W 1 to second plus W second to third minus W third to fourth minus W fourth to 1. So W equal to nRT1 log V2 upon V1 minus nRT2 log V3 upon V4. Now we know the value of W. So efficiency eta of the Carnot engine is eta equal to work done divided by Q1, the amount of heat that is uh, supplied by hot reservoir. So just put the value W, that is Q1 minus Q2. So it will become eta is equal to 1 minus Q2 upon Q1. And this is very important relation. Eta equal to 1 minus Q2 upon Q1. Similarly, we know the second relation, eta equal to 1 minus T2 upon T1. Alright, T2 is the temperature of the sink and T1 is the temperature is the hot reservoir. By substituting the values of Q1 and Q2 in the expression of the heat efficiency, that is eta equal to 1 minus Q2 upon Q1, so we get eta equal to 1 minus nRT2 log V3 upon V4 divided by nRT1 log V2 upon V1. So we know Q1 equal to nR T1 log V2 upon V1 and Q2 equal to nR T2 log V3 upon V4. We already calculated in previous slide. So just put the value, you will be get eta equal to 1 minus T2 upon T1 log V3 upon V4 divided by log V2 upon V. Now we will learn relation between volumes for adiabatic process. So since step second to third is the adiabatic process, there is a exchange. There is a no exchange of heat between system and its surroundings. So by using the temperature and volume relation for adiabatic process, and that relation is T1 V2 raised to the power gamma minus 1 is equal to T2 V3 raised to the power gamma minus 1. So it will be become V2 upon V3 is equal to T2 upon T1 whole power 1 divided by gamma minus 1. Similarly, for step 4 to 1 is an adiabatic process. The relation will be T2 V4 raised to the power gamma minus 1 is equal to T1 V1 raised to the power gamma minus 1. So rearranging the term, it will be V1 upon V4 is equal to T2 upon T1 whole power 1 divided by gamma minus 1. So now using the equation 11.24 and 11.25, we can write V3 upon V4 is equal to V2 upon V. Alright, when we comparing both equation, the relation comes out V3 upon V4 equal to V2 upon V1. Calculating efficiency. So by substituting the values V3 upon V4 is equal to V2 upon V1, we get eta equal to 1 minus T2 upon T1 log V3 upon V4 divided by log V2 upon V1. So we get eta equal to 1 minus T2 upon T1. And this is the efficiency of the Carnot engine in terms of temperature. So this is very important relation. All right. Carnot engine efficiency. Using the expression of Q1 and Q2, calculating the ratio Q2 upon Q1. So Q2 we know mu R T2 log V3 upon V4, whereas Q1 is mu R T1 log V2 upon V1. So taking the ratio, you will be get Q2 upon Q1 is equal to T2 upon T1. Alright, as we know, V2 upon V1 is equal to V3 upon V4. So just this from this expression, V3 upon V4. Here put the value of V2 upon V1. So both log terms are cancelled out. Similarly, mu r cancel out, and the remaining terms is T2 upon T. All right. So the expression is Q2 upon Q1 equal to T2 upon T1. Now, eta equal to 1 minus T2 upon T1. So eta equal to 1 minus Q2 upon Q1, because we know Q2 upon Q1 equal to T2 upon T1. So from this uh, equation, we can write eta in terms of heat. Now, here T1 and T2 must be in Kelvin, not in degree Celsius. All right. Carnot's theorem. Carnot's theorem consists of two parts. First, no engine working between two given heat reservoirs can be more efficient than a Carnot engine working between the same two reservoirs. This means the Carnot efficiency eta equal to 1 minus T2 upon T1 is the theoretical maximum. Second is the efficiency of Carnot engine is independent of the nature of the working system. And this line is very important. All right. Implication to increase the efficiency of heat engine, either increase the source temperature T1 or decrease the sink temperature T2. So this is the conditions to increase the efficiency of heat. Limitations of Carnot cycle analysis. Carnot cycle analysis has a few limitations. First, assumes reversible operation. Real processes are always irreversible. This is first limit. Second, ignores finite time effect. But in reality, engines must operate at finite speeds. Third, neglect practical constraint. But in reality, material limits, cost conditions are to be considered. Fourth, steady state assumption. Transient effects not considered. So these are the limitations. Now, example, a Carnot engine operates between a hot reservoir at 500 Kelvin and a cold reservoir at 300 Kelvin. Calculate a efficiency. Second, work output if 1000 joule of heat is absorbed from hot reservoir. See, the heat rejected to the cold reservoir. All right. To solve this question, we will use the concept of Carnot engine and their formulas. Let's see the solution. Given hot reservoir temperature T1 equal to 500 Kelvin, cold reservoir temperature T2 equal to 300 Kelvin. Heat absorbed from hot reservoir is Q1 equal to 1000 joule. All right. Now, first we have to calculate the efficiency, Carnot efficiency. So we know the formula of the calculate the Carnot efficiency, that is eta Carnot is equal to 1 minus T2 upon T1. So just put the values of T2 and T1 and solve. You will be get 1 minus 300 divided by 500. After calculating, you will be get efficiency of the Carnot engine is equal to 1 minus 0.6. It will be equal to 0.4. It means the efficiency is 40. Yes or no? Now, second, let's see. So second, we have to calculate the work. So we know the formula of eta, that is W upon Q1. So to calculate the W work done, so just multiply the efficiency and heat, or we can say Q1. So it will be W equal to 0.4 into Q1, that is 1000. So when we calculating this, you will be get 400 joule. All right. Similarly, we will calculate C part, heat rejected to the cold reservoir. So the relation between Q2, Q1 and W is Q2 equal to Q1 minus W. So Q2 equal to uh, value of Q1, that is 1000, minus value of W, that is 400. So when we subtracting this, you will be get Q2 equal to 600 joule. All right. So these are the formula based question. Now verification. So Q2 upon Q1 is equal to 600 divided by 1000. When we solving this, you will be get 0.6. All right. Similarly, T2 upon T1 is equal to 300 divided by 500 equal to 0.6. It means both are same. So we can say Q2 upon Q1 is equal to T2 upon T1. So ratio of heat rejected to the heat absorbed equals to the cold to hot reservoir temperature. And this confirms it is indeed a Carnot engine operating at maximum possible efficiency of 40%. All right. Now we summarize. A reversible process is one where all changes can be exactly reversed. It means it return to original state. While irreversible processes cannot return to their original state, like friction, heat transfer, these are the uh, factors that oppose. Carnot engine represents an ideal heat engine that operates between two temperatures, reservoir temperature and sink temperature. Carnot cycle consists of four reversible processes: isothermal expansion, adiabatic expansion, isothermal compression, and adiabatic. Carnot engine efficiency is given by eta equal to 1 minus T2 upon T1, where T1 is the source temperature and T2 is the sink temperature in Kelvin. And this is important, in Kelvin. According to Carnot's theorem, no engine can be more efficient than a Carnot engine operating between the same temperature reservoir. Efficiency of a Carnot engine is independent of working substance and depends only on the temperature ratio of the reservoirs. Alright, now we have some practice questions. This is homework for you. First, an ideal Carnot engine operates between temperatures 400 Kelvin and 300 Kelvin. Calculate its efficiency. We know the formula, eta equal to 1 minus T2 upon T1. Just put the values and you will be get the efficiency of the Carnot. Second, a heat engine absorbs 800 joule of heat from a hot reservoir. It means Q1 equal to 800 joule at 500 Kelvin. T1 equal to 500 Kelvin and reject some heat to a cold reservoir at temperature T 200 Kelvin. It means T2 equal to 200 Kelvin. What is the amount of heat rejected to the cold reservoir? You have to calculate the Q2. You uh, so use the formula eta equal to 1 minus T2 upon T1 and 1 minus Q2 upon Q1. So when we equate both, you will be get the value of Q2. Third, the temperature of the hot reservoir in a Carnot engine is 400 Kelvin. If the efficiency of engine is 25%, what is the temperature of the cold reservoir? So here you have to find out the temperature of cold reservoir. So you have to find out the true or false. The efficiency of Carnot engine depends on the working substance used. If a Carnot engine operates with an efficiency of 30%, if the cold reservoir is at 300 Kelvin, what is the temperature of the hot reservoir? Alright, so these are the practice questions. So please solve all the questions. Thank you for your attention.